Okay. All right. So first, I want to thank the organizers for inviting me, not inviting me, for giving me an opportunity to talk at this workshop and tell you about the work we did recently about multi-level analytical models for solid solutions. And this was done with basically by my students, Suhas Yadav and Or Shafir, and my postdoc, Atano Samanta. And so when we think of ferroelectric perovskites, so many target properties are achieved by modifying the composition. So we take our lead titanate, which is a very basic material, and we add PMN, or we add PIN and PMN, and then we get something which is a single crystal with large electromechanical coupling and a strong D3C. And so compositional variation is basically the standard means by which we can adjust the properties to what we want. Right. So this conference is organized by Materials by Design. And so one of the means of design is to change the composition. And so the fundamental goal of material science is to understand how does composition of a material relate to structure, and then how the structure relates to properties. And besides this fundamental point, of course, in terms of applications, if you know the relationship between the composition and structural properties, it's very helpful for design of new materials. So we need some sort of way to link the composition, structure, and properties. Okay, so as theorists, for the last 25, 30 years, we've been using DFT. And DFT is a very useful tool for doing exactly this, for taking composition relating to structural properties. But when we go to big size solutions, say like over here on this diagram, we'll say something like you go from binary to ternary, quaternary. So the cost of exploring these phase diagrams goes up very, very quickly. And so this is log scale and CPU hours, and this is kind of a cartoon. But as you go to higher and higher dimensions of phase diagrams, you have more and more compositions to explore. And because you have, you can no longer use small supercells, so each individual calculation also takes longer. So doing high throughput DFT becomes very quickly impractical when you go to, say, ternary, quaternary, or quinternary solid solutions. So you can say, okay, well, then let's do machine learning, right? This is very hot for the past 10 years, so we'll do some calculations, maybe we'll get ourselves database on this level, and then we'll use machine learning to get us to where we want to go. It's still a problem for two reasons. Number one, because you still need a lot of data to parameterize your model, and secondly, because even if when you have your model and it works, which is also a question, but even if it works, it does not really provide insight. And as scientists, we'd like to understand, why our model tells us what it tells us, and not just kind of trust that it does the right thing. And so what we really would like to have, at least as a first approximation, is some analytical model that links composition, structure, and properties in a mean-field way. So I will tell you composition, if you tell me the composition of my perovskite solid solution, so I will tell you the property of interest that we care about. And so this is what we try to do for lead-based or lead titanate-based solid solutions. And so here's our approach. We look at this kind of multi-level model where we start at this bottom level, where you have this alphabet soup of different elements in your composition, in your material, let's say bismuth, lead, titanium, zirconium, all sorts of B and A say cations. And you say, okay, well, let's look at different cations over here, and let's look at their individual atomic properties. For example, that we know are important, let's say ionic size, or valence, or let's say over here the electronegativity, which basically tells you how covalent the bond between the B cation or A cation and the oxygen is going to be. And then we can say, okay, from there we'll go to structure on the unit cell level, which is basically the displacements of the A site and B site cations. And of course, when you know that sorry, what did I do? Okay, and that gives us the polarization. And from polarization, which is a unit cell level property, we go to something, say, on nanoscale level, which is the domain walls, which are, first of all, very interesting in themselves, and also are crucial for understanding the next level. And the ultimate level, perhaps, as you want from property standpoint, which is the transition temperature and, let's say, the corrosive field of our solid solution. So to go from here to here in one shot is pretty difficult, but if we go every single level, the links here are probably understood and can be encapsulated in an analytical simple fashion. Okay, so that's what we did for solid solutions of lead titanate, and let's see how it works. Okay, so the first level we have is, again, going from the element identity, and it's the ionic properties or the atomic properties of the element to the displacements. And so we know from DFT calculations that if you have big ions and ions which are less covalent, they will displace less. If you have ions which are small and more covalent, they will displace more. And this actually is also can be derived from this Weber coupling theory paper published in PRV 2015. And in the end, you have an expression for the sort of the intrinsic displacement, how much the ion wants to displace in its O6 octahedron, and that's proportional to the stiffness, which is related to ionic size. and the delta over here, which is related to the electronegativity of the cation, because this is just the difference in eigenvalues between the oxygen 2p states and the transitional d states. And so from here, you can derive this expression that your sort of intrinsic preference of the cation to off-center is just proportional to some power to r to the minus 2 with some coefficient and the electronegativity squared. So if we fit these parameters to our GFT data, we get a pretty good agreement. So we can see that, yes, in fact, we can link the level from here to level from here. But of course, that's just the first level and tells us how much does each ion want to off-center by itself. Or let's say in a very lead-tight nitrogen environment. But of course, in a solid solution, these ions are going to be all coupled. Like if you see a cartoon over here, if you have titanium and wants to displace a lot, and in front of it's another titanium, so they all couple their displacements and move forward by a big amount. But if in front of titanium is this rather large indium atom, so then this is going to block the displacement of titanium because of the through oxygen coupling between these displacements. So we need some way to characterize the coupling and the influence of one cation on another cation. And we do this through this very sort of simple, this is perhaps an ad hoc model, but again, it's kind of taking the idea, let's make it simple, sort of first order approximation, and we'll say that the actual displacement of the cation in the solid solution is its preferred displacement in sort of in the lead-tight nitrogen environment times sign modification factor, which itself is the function of the average structure or average composition of the solution. I'm not going to get too much into this form. There's another expression which is more complicated that takes into account the influence of the ionic size on the displacement of the A side cations. But once we have the influence of the composition taken care of, and we can predict the displacement of each individual cation in the solid solution, we can very easily get polarization by multiplying by the Born effective charges. So this, again, assuming that we know these kind of parameters over here, and this should be labeled by different, this will be like A1 and A2. No, actually, no, this is fine. So if you know these parameters, then we can take the composition and we can predict what are the individual displacements of the cations in the solid solution. Okay, and that gives us polarization. And then we go to the next level, which is polarization and domain walls. So again, domain walls are hard to do in solid solutions because you need very big cells. But if we use some sort of analytical model, which is described in this paper over here, and what we showed is that for a sigma 71 rhombohedral domain wall and a 90-degree tetragonal domain wall, there are two contributions to domain wall energy. One is the electrostatic energy of dipole-dipole interactions, and of course that scales as p squared. And the second one is the repulsive energy, which has a p squared component, and also in this region of polarization, sort of like a flat constant level. So we can say that in this region of polarization, sigma 71 is p squared plus some small constant. The same thing for sigma 90. So this now tells us, given the composition and therefore given the displacements and therefore given the polarizations, you can estimate the domainal energies for a given solid solution. And why these domainal energies important? Because they give us the next thing, which is the transition temperature. So what's the connection between domain walls and transition temperature? So there's a simple argument to be made, but in this case, I don't have to make it even so much because we saw that from previous talk over here, that if you look at the high temperature sort of ferroelectric-like state, it's actually not a non-polar state at all. It's a locally polar state, which is reminiscent of the domain wall. And in another talk, we saw that if you use the energy of the domain wall, you can actually predict the TC from some sort of statistical model. So domain walls are clearly important. And finally, there was this TM results for barium titanate from 2021, which again show that in the high temperature ferroelectric phase, just above TC, you have these domain wall-like structures. So if you characterize the difference, the energy difference between the ferroelectric state and the paraelectric state as proportional to the domain wall energy, so it's natural to kind of wave our hands and say, well, TC is proportional to sigma 71 or maybe sigma 90, which means that if you have a bigger domain wall energy, you have a bigger TC, and we can kind of see that TC should scale as sigma 71. Well, is this correct or not? Again, we know how sigma 71 scales the polarization. It's a small constant plus AP squared. So therefore, we can hypothesize that, again, for the range of polarizations we're interested in over here, TC should be some small constant plus AP squared. So let's look at the data. Here we have DFT polarization calculated over here on the x-axis, experimental DC on the y-axis, and we can see that we can fit for, let's say, bismuth-based systems or lead-based systems, solid solutions, we can fit them to a normal AP squared expected relationship, but you can also see that the fit is not so good, right? You can see that here it's above the line, here it's below the line, and here it's the same thing. And this is because it's not actually correct, it's correct dependence. The correct dependence is C plus AP squared. And you can see it better on the spot over here, where this is P squared on DFT on the x-axis and experimental TC on the y-axis. So here is a fit to the p-squared straight, and you can see that it crosses some points, but most points are really not fitting very well at all. And C to plus AP squared does look quite much better, except for these few outliers. So again, the domainal energy tells us or how TC is going to behave in these solid solutions as a function of polarization. Okay, so now we can go what they call in machine learning end-to-end, I think, and we can say, well, let's look at our whole model starting from here. We know the composition, we know based on the composition what the displacements and individual cations are, if we know the parameters, and then from these once we know these displacements, we can calculate polarization. From polarization, we get the sigma. From sigma, we get TC, and of course, there are some parameters that have to be fit for each one of these links. So what we're going to do right now is we're going to take our model for each step of the way, and we're going to fit all of these different parameters to the experimental TC values for a whole bunch of different bismuth-based solid solutions. So this will say bismuth zinc titanate, lead titanate, bismuth magnesium tungstate, lead titanate, etc., etc. And again, we're going to take the TCs and we're going to fit this to the whole multi-level model and try to find parameters that give us the best match with the experimental data. And you see it actually works quite well. So here's the polarization predicted by our model, and here's experimental TC for all of these different solid solutions. And once again, we see that this idea of TC being proportional to a small constant plus A plus P squared, again, in this range, and I want to emphasize it's only in this range. Below this range, we don't have any data, and it probably goes like this. Okay, but in this range, we can get away with just saying a small constant plus P squared. It actually works quite nicely, despite the fact that the model is quite simple. So we can now link a composition of the solid solution and TC to fairly good accuracy. Okay, so now let's go to the next thing, which is the corrosive field. Okay, so for rhombohedral ferroelectric, corrosive field is governed by the energy of the critical nucleus, right? This is sort of standard theory that you have the U star, that's the critical nucleus for activation of the domain wall, and it's proportional, for, say, for rhombohedral ferroelectric, the sigma 71 squared divided by applied electric field times polarization. And since sigma 71 is roughly proportional to P squared, we can get that the corrosive field is roughly proportional to P to the third. And since TC, again, is roughly proportional to P squared, ignoring the small constant, we can use LGD to show that corrosive field at 300 Kelvin should be proportional to TC of the material minus 300 times to the 1.5 power of 1.5. Okay, so we can define this delta TC, the difference between the TC of the material and 300 Kelvin. Okay, and then we can say, all right, so this is our suggested relationship in the corrosive field and the TC of the material, which again, as I mentioned before, can be predicted for polarization, which can be predicted from displacements. So here we plot a whole bunch of different single crystals, and we need to use single crystals because that gives us more of an intrinsic corrosive field that ignores the effects of grain boundaries and things like that. And we can see that it's a very good fit to this relationship. So this is the line for the TC, for the delta TC to the 1 to the power 1.5. And you see that it's pretty good fit with some outliers, which are inevitable because even single crystals are not perfect. And they have, for example, here, if you have manganese doping, you probably have some effect of pinning of the domainal motion and gives you either, say, a higher corrosive field, or maybe it actually goes with lower corrosive field. But again, for more or less normal single crystals, we have pretty nice relationship. So again, now we can go from displacements to polarization to the domainal energy, transition temperature, and corrosive field. So what can we do with this besides just fitting these data? We can look at ceramics. Okay, so in ceramics, we have two effects. We have the intrinsic effect of the material, how much material wants to switch. And we also have the effect of the grain size or grain boundaries. And you can see that if I plot now the ceramic data versus this delta TC, it still roughly follows this trend, but we have a lot of outliers. Okay, and so now we can say, okay, well, let me evaluate the difference between what I expect the corrosive field to be based on the TC and what it actually is, and then plot that versus grain size to evaluate the influence of grain size on the corrosive energy. And we did this for the few systems that we have data for the grain size. We found an interesting thing. If you look at the systems which do not contain scandium, so there's a very clear relationship, there's a very clear relationship between the this enhancement of corrosive field and the grain size. And as expected, if you go to higher grain sizes, we go to the single crystal limit, and this difference becomes quite low. However, for scandium-containing systems, even if the grain size is very small, the difference from the single crystal corrosive field value is quite low. And this suggests that even for small grain sizes, the scandium systems are very well textured, the grains are very well aligned, and this, we think, might be an explanation why PSPT solid solution has a very high DC3 that has not been matched for its TC by any other solid solution. Perhaps it's just a question of having a very good alignment in the ceramics sample as opposed to other materials where such alignment is missing. So finally, one last thing, and which is the people have talked about anti-ferroelectrics and designing anti-ferroelectrics. So we propose a very simple criteria that if you take any proposed compositions you want, we tested this on PCT and double perovskites, and you look at the anti-ferroelectric phase and ferroelectric phase in TFT, and you look at the average displacement of the B cation in the ferroelectric phase. So if this average displacement of the ferroelectric phase calculation is less than 0.11 angstrom, so the anti-ferroelectric phase will be stable. If it's bigger, then the ferroelectric phase will be stable, as you can see on the plot over here. So this is the DFT calculated average displacement, and these are different systems known to be either anti-ferroelectric and ferroelectric. And there's a dividing line, and PCT is right over here, okay, in the different compositions. And now we can say what something is going to be anti-ferroelectric or ferroelectric just based on the simple local criteria. So finally, my conclusions are that now for lead-based titanium solid solutions, we have relationships in composition and all of these different target properties that we want, okay, with Curie temperature, polarization, corrosive field, say O6 tilt magnitude, displacements, and even the compositional phase transitions, we'll say RT MPB or anti-ferroelectric ferroelectric. What we don't have and what we'd like to have in the future is some sort of a model for the DC3, because of course that's the ultimate target property for piezoelectrics, but that's much harder because it involves things possibly that extrinsic effects, and we don't really know how to do it yet. And of course, the next thing to do after lead tightening based stuff would be to do lead-free solid solutions. And thank you.
Thank you. When you do compare the data, I think trying to define a correlation the depth of the technology well. At some point, many years ago, we actually did like an artificial experiment with models. We modified the models to keep the spontaneous polarization magnitude constant, but changes the well, the depth of the well, and vice versa. Change the spontaneous polarization magnitude that keep the depth of the well constant.
Right.
We got convinced that the depth of the well correlates more strongly.
So you see, it's hard to evaluate because I mean I understand, but the reason why I don't think it's correlated to the depth of the well is because again, if you think of the ferroelectric to ferroelectric phase transition as just going to this point in the middle of double well, then of course it will be correlated. But again, now we have plenty of evidence that that doesn't happen. That we have what happens is you go some sort of domain state. And therefore, it's domainal energy that should be proportional to the TC, right? There's an analogy also in metals. If you look at the melting point of a metal, it actually correlates very strongly with the vacancy energy. Because the same idea that if you have a metal just above the melting point, it's not just like a bunch of atoms flying around by themselves. It's sort of like looks like a vacancy inside of a metal structure.
I might say that, but do you think that the one energy will correlate in the depth of the well? Well, it depends on the way you that, right? I mean, but as the depends on the kind of.
I mean, this a long time ago. I tried to correlate with the double well energy and it didn't work. So perhaps it also has to do with how you especially if you have a solid solution, how they calculate double well in the presence of O6 tilts, without O6 tilts, right? So it becomes very complicated, and this seems to be like a much simpler criteria.
Is there any more question? I have a quick one.
Yes.
How easy would it be to do that in CPUs?
So thin films, I think, will be exactly the same. Like let's say the TC of thin film. The only question is what happens when you strain. So actually, in this paper, we show that we can modify the displacement based on strain using some sort of relationship, but you actually more or less predict the evolution of TC and therefore the corrosive field for the thin film as you strain the material. So it's a question. Essentially, what this says is that your collective properties, like corrosive field of TC, again, without looking at grain boundaries and things like that, are governed by the polarization of the material. So if you know how polarization evolves with strain, you know how TC and corrosive field will evolve, again, to first approximation. Okay.
Very interesting. Thank you. Thank you again. So now it's Wei from the University of Arkansas. We're going to talk about nonlinear.
So clear?
Ferroelectrics.
Oh, what's this?
Oh,
On both sides. So one here, one here.
Mhm.
This, I guess, in your pockets.
Where is the mouse?
2 minutes before the end, okay?
Okay,
When you have 2 minutes left.
okay. How can I use the laser?
No, I think, no, this is for audio.
Where is the laser?
Laser is-
Oh, okay. Wait, hello? Doesn't work?
I was.
Oh.
Which presentation is yours?
Talk with. Here. Yeah.